This is work that from IBM Research, and this is work with some co-authors, Vasileios Pappas and Hani Jamjoom. And like it said, the title is AIN, a blueprint for an all-IP data center network. Okay, so as you all know, when you think about a cloud computing environment, there are certain requirements or constraints that you have to have for when designing the infrastructure, and so the network is no exception here. And mostly these things are, there's not really any surprises in the list of things I have up here. So things like the network has to scale, it has to perform, network mobility. So this is allowing a VM to run on any host at any time, and also address virtualization or the ability to support multiple tenants that may want to use the same IP addresses at the same time. And so when thinking about how to design a network architecture in a data center to address all of these concerns, it's not really clear which network abstraction layer you should focus on. So really there's kind of two candidates, I guess. So the first one is layer 2, so Ethernet. And this was kind of developed for local area networks. Its strengths, the automatic configuration means that it's great for things like VM mobility, but it isn't really great for scale due to things like broadcast protocols like ARP that are happening, and not that efficient use of all the links. On the other hand, you have layer 3. And so like IP, and here you have scale. So this was designed to internetwork between lots of smaller networks, but typically you have these topologically significant addresses. The IP addresses encode somehow your location, and this has always kind of, or typically limits mobility. And so instead of kind of keeping a separation between these two network abstraction layers, current approaches tend to blend layer 2 and layer 3 when they try to achieve those goals that I had on the previous slide. So, for example, they may encapsulate packets so that they hide the MAC addresses of the VMs from the switches. They may introduce things like distributed directory services to try to alleviate some of the overheads from broadcast. And there are a number of approaches. I just listed a couple down here: Trill, Portland, VL2, that have this flavor, which I would call kind of blending the layer 2 and the layer 3. Of course, the downside of blending these two is that there's no longer a clear kind of separation between the two layers, and this leads to some increased design complexity. And so for this work, the question that we kind of asked is can we keep layer 2 and layer 3 separate and really just focus on layer 3 to give us all these things that we wanted? So use Ethernet just for things like framing and synchronization, medium access control, and then use IP for things like the addressing, the routing, the mobility, the multitenancy. And really that's kind of what we explore in this paper. So the basic approach is you take your data center network and you make this a complete layer 3 network. So this is an IPv6 network, and you push you push the routers all the way out to the edge. So now each hypervisor would run, instead of a virtual switch, it would run a virtual IPv6 router that forms this all IP network. And of course, this network would then need to do things like map the VM addresses into this all IP network space, advertise the routes to the routing, support the mobility and the multi-tenancy, basically all the things that we require in a cloud setting. And so, for the rest of this talk, I'm going to kind of go through an exercise of going through each one of these aspects of the addressing, the routing, the mobility, the multi-tenancy, if you had this kind of all IP network in the data center. Okay, so the first thing is the addressing. So really, there are two address spaces in AIN, or there's the host address space, and this is the one that the VM sees. So this could be IPv4, IPv6, And really, it's only visible to the VMs and the hypervisors. So this is not what is kind of routed through the network. At the same time, you have the network address space, and this one is kind of invisible to the VMs, but this is how, so this is only visible to the hypervisors in the network, and this is how packets actually get routed through the data center. So to understand how these address spaces are related, I'm just going to go through a quick example translation of how to convert between the host address space and the network address space. Okay, so let's say that the VM is in a host address space that sees IPv4 addresses. So the VM is going to send a message to an IPv4 host address. So the first thing that happens is that host address becomes the low 32 bits of the network address. Then the hypervisor adds what we call tenant and network tags based on the VNIC metadata. And so each VM is associated with a tenant and also a network belonging to that tenant. And so these tags, you can think of those as essentially giving this last 64 bits that I have on here essentially is a unique identifier for this address. So it's a tenant ID, a network for that tenant, and then the IPv4 host address that it has. And then to fill out the network address, we compute a consistent hash over those 64 bits to get these top 64 bits, which are the home hypervisor address. And I'm going to describe what the home hypervisor is in just a second. But what you can see here is that now we have a 128-bit IPv6 address. Okay, so the home hypervisor, what's that all about? So each VM has this concept of a home hypervisor. And essentially what the home hypervisor does is it's the entity that owns the network address for the VM's host address. So if you think of a packet being addressed to a VM, this would be the home hypervisor is kind of, so it maintains this mapping to the VM, which may be on a different hypervisor, but we can talk more about that in a minute. But essentially, it knows how to get that last hop. It knows how to get how to look at one of these addresses and figure out where the VM is. So by computing this consistent hash over those unique identifiers, this essentially assigns a home hypervisor to each VM in a pseudo-random fashion. So as an example, so now we understand. So now once you have this network address space address, and you want to convert this back to a host address, that's much simpler. The home hypervisor would examine the tenant and network tags to figure out which tenant and network the VM belong to, and then deliver the message to the VM with the rest of the prefixes kind of stripped out. So, okay, so that's how the addressing works in AIN. The next part that I'm going to talk about is routing, or how these packets are going to be routed through this all IP network. So this diagram here is of a typical data center network architecture. So at the bottom here, maybe you can't see all the lines. There's some little lines in there. It's not really too important. So at the bottom you have some servers. You have some access switches that they're connected to, aggregation switches, core switches in the back there. And so when we think about routing, if these are all switches, if we turn all those into routers, this is kind of what we want to do, right? So the idea is, well, why don't we use a routing protocol like OSPF, and other protocols could probably be substituted here, but this is the one that we put a little bit of thought into. So the idea is, okay, let's map that data center network architecture in that previous picture to OSPF. So we're going to run OSPF on all the switches and the hypervisors. And then we're going to just divide the data center network into OSPF routing areas so we can get some scalability. So this is what's going to limit the link state advertisements between the areas. And so, okay, you can't see it, but there are. I tried to highlight some areas. So this at the back here would be one area, which is the backbone area. this right here would be area 1. This is area 2. The colors aren't working so well on the projector, but what I was trying to show with those things is that these OSPF routing areas essentially can be related to the kind of physical topology of the network. So, and here's a table of how the mappings would work. So that backbone area at the top, that would consist of the core and the aggregation switches. The access switches and the servers are these point of delivery areas. So that was the area 1, area 2 that I had along the bottom. And so really what that corresponds to is each kind of rack or set of racks, which would form a point of delivery POD area, can corresponds to one of these OSPF routing areas. And then the aggregation switches are essentially area border routers in the OSPF terminology. And so what does that get you? So using this, using layer 3, what does that get you? And so really what we would want is that it gets us scalability, because that's what layer 3 is supposed to be good at. So these tables over here, the numbers aren't too important, but it's essentially what we tried to do is take an example data center network and see kind of what the link state database was going to look like, and really for 1024 256 PODs, they were reasonably sized. So things like 12 to 50 updates per second. The other benefit of using OSPF is that we get multipath support. So equal cost multipath routing, ECMP. We'll do the load balancing, not just based on the hosts, the end host, but also based on the VM addresses, because the VM addresses are now somehow exposed to the actual network. Okay, but we do lose something though, because we lose the broadcast support, because now we're going to layer 3. We're kind of ignoring this, and this is one of the things that layer 2 is all about. So the way that we view that is we view the broadcast as something legacy, so it's not given by default. And if a legacy application wants to broadcast, they can request a special broadcast-capable prefix. And then once they do that, the hypervisors will then emulate broadcast domains by encapsulating packets and either unicasting or multicasting the packets to the hypervisors that share the broadcast domain. Okay, so that's the routing aspect. So next, the mobility aspect. So layer 3 isn't typically thought of in terms of mobility, but there are things like mobile IPv6 and proxy mobile IP, and this is what's used by the LTE and 4G cellular networks. Essentially, so what proxy mobile IP has is these two concepts: the mobile access gateway and the local mobility anchor. So the mobile access gateway is essentially the thing that is currently hosting the VM, or the thing that would be currently talking to your cell phone or whatever. So in our situation in the all IP network, the hypervisor currently hosting the mobile VM would be running the mobile access gateway for that VM. The local mobility anchor, on the other hand, would be kind of like the home node. So that's the home hypervisor of the VM. And so the idea is that if you were sending a message to a VM, first it would go to the local mobility anchor, which is the home hypervisor, and then the traffic would then be redirected to the mobile VM to its mobile access gateway. So it's probably easier to see in a picture, so maybe I should have put this up a minute ago, but yeah. Okay, so in this example, we have VM1 who's sending a packet to VM2. So VM1 sends the packet through the network, goes to the home hypervisor of 2, where the LMA is, the local mobility anchor for 2. There's a GRE tunnel that is established between the LMA2 and the mobile access gateway MAG2. And so then the home hypervisor forwards this packet through the tunnel so they can eventually get to VM2. Okay, so of course this looks like it has pretty high. It's got this this home hypervisor that's kind of in the way, and if that, let's say VM1 and VM2 are fairly close to each other, but home hypervisor is somewhere else, then maybe you wouldn't want to take that extra indirection. We think that you could probably do something like distribute the LMA between multiple hypervisors to get to sort of eliminate that that overhead. So in this picture, we have the home hypervisor. It's duplicating replicating this LMA, and so now when VM1 sends the packet to VM2, this local LMA copy will have a tunnel established to the MAG, which will eventually get to VM2. And so, okay, so what does this give us? So using proxy mobile IP for the mobility in the data center network, this allows us no end host modifications needed for mobility. It's possible that this can even apply to mobility across data centers, as long as you can establish a GRE tunnel. That's all that really needs. So anywhere that you have one of these IPv6 addresses that is addressable by another data center, then you can make one of these GRE tunnels, and things should just work, right? The other thing is that ECMP still works because it is aware of GRE protocol headers. Okay, so that's the mobility aspect. So finally, we have the multi-tenancy. Okay, so multi-tenancy, we take a point of view that really the thing that we need to do for multi-tenancy is just make sure that these host address spaces are really isolated. And we take advantage of the fact that end host VM firewalling is fairly common. So instead of the end host, the end VM running the firewall, though, we can run this in each one of the hypervisors. And what this allows us to do is place outgoing rules that can prevent IP spoofing attacks, so we can make sure that if a packet is sent, then it is sent out with the right address. And also incoming rules, we can make sure that the tenant end or network tags are always followed for incoming traffic. Okay, so just before concluding, it looks like I'm probably going to be a little bit short, but so I thought I'd mention a little bit about the related work, just to put this in a little bit of context. I mentioned some of these at the beginning that blend this layer 2 and layer 3, and so the way that I kind of think about this is that you have these different design points. So Trill is essentially taking a layer 2 approach and then adding some layer 3 aspects to it. It's adding the link state routing at layer 2. VL2 has a lot of similarity to what we are thinking. They use OSPF and ECMP in the data center in the kind of core network. But their focus is really on supporting this virtual layer 2 abstraction, where we feel that a kind of unexplored point in the design space is to push all the way to the layer 3 instead. Portland kind of pushes all on the other side and says, what if you just route based on layer 2, and then you have VXLAN and VGRE, which are some of these encapsulation formats for preserving this layer 2 model. So just to summarize, so I've described AIN, which is an all IP network, and the idea here is really this question: can we simplify some of the data center network architectures by focusing only on layer 3 instead of trying to blend between layer 2 and layer 3? And just by looking at some of the things that layer 3 already provides, it seems to provide scalable routing, equal cost multipath forwarding, this network-based mobility management. And so, I think that the question that we really want people to think about is whether or not, whether these blended approaches are really needed, or whether layer 3 is actually enough for a scalable data center network architecture. Okay, thanks.
Keichima from IAJ. I have a question about addressing mechanism.
Mm-hmm.
Could you show the slide that explains addressing? In the figure, yes, this one. Yeah. I don't understand how do I get IPv6 address? So how do you manage the IPv6 addresses in virtual machines?
Okay, so the IPv6 addresses are done slightly differently. So we don't use the same address translation this way. There's two cases. So if the data center is the one that owns the IPv6 address, then it gives off it gives that address to the guest from a pool of addresses that belong to the home hypervisor for that VM. So there may be a pool of available addresses, and it can give one of these to the VM. If the VM has its own, then we use that. Then we allow it to use that one by exposing that one through. Did you understand?
Yeah. Okay. I see.
So again, another question regarding the addressing. Mm-hmm. So you mentioned that essentially you're able to get a consistent hash based on the VM ID, essentially a tenant ID, and map it to a particular IPv6 address for the network. Yeah. Right. So but this fundamentally is kind of, in a sense, flat, essentially using flat addressing, because you don't have any hierarchy or aggregation. Right. So how do you achieve scalability in terms of the IPv6 routing itself?
Well, so the assignment of the addresses to the so I think that computing this address, I think, like essentially the way we think about it is we're just mapping VMs to these things, right? So in the network, so assuming nothing moves, I think that you still have the hierarchy in that respect, right?
You would have hierarchy if you had location-based addresses, for example, right? But in this case, your addresses are not location-based. They're based on a consistent hash of whatever addresses the VM chose to use.
Right, but each one of these home hypervisor addresses, so the home hypervisors would kind of own parts of the address space, which did fit into a hierarchy, right? Okay. Does that make sense?
Okay, we can probably take this offline.
Okay.
Okay.